We all know people who practice a skill intensely, yet never seem to improve. A new piano player, for instance, might spend hours repeating the comforting parts of a song they already know. They generate a lot of physical motion, but no real progress. Real progress requires what psychologists call deliberate practice. It is the frustrating, methodical process of isolating your weakest areas and attacking them directly. Machine learning optimization operates on the exact same principle. If your model is failing, you can spend days tweaking parameters, even swapping architectures, or feeding it more data. But without a diagnostic system to identify exactly why it is failing, you are just blindly repeating the parts you know. Let's build that diagnostic system. This is a 2D plot showing a very small dataset. We're going to map a variable, like the size of a house on the x-axis, to its corresponding cost on the y-axis. Step 1 is to completely scramble this data. Datasets often arrive ordered by date or location, and training a model on ordered data will hard-code artificial biases into your results. Step 2 is the split. We isolate 60% of these points to train our model, and we lock the remaining 40% away as a hidden test set. We do this because the ultimate goal of a machine learning model is generalization. We need it to accurately predict house prices it has never seen before. Let's fit the simplest model to our cyan training points, a flat line with zero slope. We measure this model's failure by calculating the squared distance between our actual data and the line's prediction. The total error hits 1500. That error rate is too high, so we increase the complexity of our model slightly. We adjust the slope to follow the general trend of the data. Immediately, the total error drops down to 3.6. That initial flat line lacked the structural flexibility to capture the actual shape of the data. When a model is too simple to learn the underlying pattern, it is underfitting. In machine learning, we diagnose this condition as high bias. If adding complexity reduced our error, you might think a highly complex curve could drive our error down to 0. And on the training data, it works. The model contours perfectly, giving an almost perfect score of 1.69. But the real test is generalization. Let's bring back our hidden purple validation points and see how our complex curve handles data it hasn't memorized. It fails completely. The validation error spikes to over 900. This massive discrepancy between a near-perfect training score and a broken validation score is called the generalization gap. Our model learned the training data so aggressively that it memorized the random noise. Now it is wildly sensitive to any new information. This is overfitting, and we diagnose it as high variance. This graph maps that exact relationship. As model complexity increases along the bottom, we leave the high bias zone on the left, but eventually enter the high variance zone on the right. The total error is always a combination of its bias, variance, and the irreducible baseline noise in the data itself. You cannot eliminate error completely. The objective is to find the equilibrium, the sweet spot where underfitting ends and overfitting hasn't begun. To navigate to that sweet spot, we use a strict diagnostic flowchart. Step 1. Look purely at your training data. Is the training error high? If yes, you have a bias problem. Do not look at the validation set yet. Instead, train the model longer, add more layers, find more features, or decrease your regularization. Once you get the training error down, you move to step 2. Now you evaluate your generalization gap. Is the difference between your training error and validation error large? If yes, you have a variance problem. Your model is overfitting. Now is the time to gather more data, remove noisy features, or increase regularization. Notice the strict order of operations. You must fix bias before variance. If you have a high bias problem, gathering more data for weeks will yield 0 improvement. You have to match the cure to the disease. You now have a concrete framework. When your model fails, you don't have to guess. You check the training error, you check the generalization gap, and apply the specific adjustments required. The result is a model that strikes the balance. It captures the overall trend with a gentle curve, but it leaves enough flexibility to accommodate new, unseen data. While this diagnostic flowchart tells you exactly what to do, executing the specific variance fixes requires understanding the mechanics behind them.
Techniques like adjusting regularization or strategically culling features take practice to implement correctly. You can explore those precise methods in these dedicated guides. Machine learning optimization is a deliberate, systematic process. It is about actively managing the trade-off between bias and variance, step by step, until your model is ready for the real world.